Also, it's my pleasure to introduce next speaker. He's Larry Reed from Imperial College, also co-organizer of this workshop. And he's going to talk about Sobolev, Hardy, and CLR inequalities in 2 dimensions. So go ahead, Larry.
Thank you very much. Thank you very much for the introduction. So yes, today I'm going to be talking about some classical inequalities and introducing an inequality from spectral theory and discussing these in the critical case of 2 dimensions. And I should mention this is work supervised by Ari Laptev and done in conjunction with Lucas Schimmer. So yes, so Sobolev inequalities. So the classical kind of Gagliardo-Nuremberg-Sobolev inequality says that if your gradient is LP, then your function is LP star, where P star is the Sobolev conjugate and is an improvement on P. So basically, the integrability of your gradient gives an improvement on the integrability of your function. So we're going to discuss we can discuss 2 critical cases in this scenario. So of course, you can consider the case similar to kind of what Meng Chung just discussed, actually when the dimension kind of gets larger and larger. And in this case, you can see from the definition of the conjugate P that you kind of lose this gain of information. You just get P back when you consider the limit. And in this case, you can consider an alternative. Again, Meng Chung mentioned this, and Yao and Straight, I think, mentioned this yesterday. So you can consider log Sobolev inequalities, and with respect to some measure that you can define on very large spaces, then log Sobolev inequalities have this property where if you consider the tensorization of 2 measures, then log Sobolev inequalities hold without any divergence of the constant, with the same constant, in fact. Whereas in the case here, the constant actually diverges to infinity. And the other scenario is when the integrability of your gradient is the same as the LP integrability is the same as the dimension. And in this case, again, one kind of loses the result with the constant, and one can consider the alternative, which is one of which is the BMO embedding. That is, you have this bound here for U of a bounded mean oscillation. And of course, you could consider the case where instead of RD, you have some compact subset of d-dimensional space. And in that case, you have some nice embedding of LP spaces, and you can find some result. But today we're going to be looking at the case where dimension is equal to 2, and therefore kind of on the this kind of for functions in this kind of standard Sobolev space. And we're going to be talking about, like I said, a related inequality from spectral theory. So, but first, let's talk about Hardy inequalities. So, in dimensions greater than 3, the standard Hardy inequality says that you have some bound of the gradient, LT norm of the gradient from below by this kind of Hardy integral here. And again, you can see from this constant is sharp, the result fails in dimension equals 2. So in this case, we have quite a few different alternatives. We have the result, the Hardy inequality, it should be H, capital H there, on the half line where U vanishes at 0. Then we have, this is the standard form of the Hardy inequality. Then we have sharp inequality here with constant 4. And in fact, most of the Hardy inequalities on dimension greater than 3 are generally kind of shown using this in polar coordinates or spherical coordinates. And of course, it's just a consequence of that proof that the constant here diverges in dimension equals 2. And so we have that, and of course we could generalize it onto the half plane just by considering functions in H1 0 on in the half plane, yeah, with the positive half plane. And then another result here is kind of, again, a bit more trivial. is the case for antisymmetric functions on R2, it should be here. And in that case, we have Hardy inequalities by kind of standard results, but I think there's a nice paper of Ostenhoff and Laftev that goes over some of the sharp constants. And we have this Hardy inequality here with constant equal to 1. Now, a more remarkable result was shown by Harry Lepto and Timo Weidel, where they said that if you have a magnetic field, in particular, the Aharonov-Bohm magnetic potential field, then if your angular part of this magnetic potential status is non-integer, the flux of this this field is non-integer, then you have Hardy inequality for the in terms of the magnetic Dirichlet form on the right-hand side here, and some constant here that is related to the kind of the spherical part of the magnetic Laplacian and the eigenvalues of, and that's where this this constant comes from. So it's bounded in the case where we have non-integer flux here. So we have some Hardy inequality in a magnetic case in 2 dimensions, on the half kind of plane case, just owing to the standard Hardy inequality, and in the case of antisymmetric functions. And this is, of course, what the AB magnetic field kind of looks like, for example, of angular, some angular potential. So today, yes, we're going to talk about some sort of spectral inequality, and that will be related to the inequalities we just discussed. So we'll just need kind of one kind of easy result, really, that you probably already know of. So if you have some self-adjoint operator here that we'll assume to be semi-bounded, that is, the eigenvalues are bounded from below, or the plus, if you add some constant here, then it's a positive operator. On some Hilbert space with domain D, then if we denote by its corresponding quadratic form, little h with domain little d, then the number of eigenvalues of h below some number mu, including the multiplicity of these eigenvalues, is given by the following formula. That is the dimension of the largest subspace of the form domain, for which the quadratic form is less than mu times the norm of u for all u in this subspace. And this is kind of known by the name variational principle. I mean, it's also kind of very much the same thing as the min-max principle, or sometimes known as Glasman's lemma. So we'll use this, and alongside this, we'll also kind of use the following tool. So we might want to manipulate this formula here and say, and consider some alteration to our quadratic form, and therefore an operator, and make it smaller in some sense. And in that sense, we can bound the number of eigenvalues above by that smaller operator, or if we know the number of eigenvalues for that. Or we might consider some restriction to its domain, and again, we could bound the number of eigenvalues from above if we could then do something with that. And in order to do that, we will kind of use this kind of this partial ordering of kind of standard partial ordering of self-adjoint operators that will say that H1 is greater than H2 in the quadratic form sense if the quadratic form is associated quadratic form is larger. So that's kind of the main idea of the proof, actually, for our result, which we'll discuss after we introduce the CLR inequality. So the CLR inequality is quite a famous result owing to Michael Schwiegel, Elliott Lieb, and Gregory Rosenblum, that says if you consider some positive potential in this L d/2 integral on our real d-dimensional space, then the number of negative eigenvalues of the Schrödinger operator here is less than the L d/2 norm of the time sum constant. And this is valid in the case where dimension is greater than or equal to 3, much like the Hardy inequality or Sobolev inequalities. So a lot of work is actually kind of focused on finding optimal constants in this sense. And that's, I believe, Dubin, for example, you asked Yao a question yesterday where he was discussing a more general result, actually, in the case of generalized kind of Schrödinger operators. And you asked whether this constant known, or whether you could find it. And the optimal constant, the answer is no. There's a lot of work that's gone into trying to find this constant here, and again, no one really has any idea what the sharp constant is. Well, no one knows what the sharp constant is. We do have some ideas. And so the key thing here again is this fails in dimension 1 and dimension 2, and that's because if you consider any positive potential here in dimension 1 or 2, so any kind of could be a very singular kind of potential, but anything that's not equal to 0 is greater than 0 in some sense, then you always have one eigenvalue. So you can't have some homogeneous kind of bound in the number of eigenvalues in dimensions 1 or 2. So the CLR inequality is actually kind of an endpoint case of a more general class of spectral inequalities known as Lieb-Thiering inequalities, or kind of the trace bounds, where the sum of the gamma powers of the eigenvalues, negative eigenvalues of a Schrödinger operator here with potential v, positive potential v, is less than some similar bound here to the right on the right hand side. And this is kind of asymptotically sharp, and it's valid in the cases where gamma is greater than or equal to half, in the case with dimensions equal to 1. In dimension 2, gamma is greater than 0, and in dimension 3, gamma is greater or equal to 0. And of course, here the case where gamma is equal to 0, given that this is the kind of this is for the number of this are negative eigenvalues, is actually equivalent to the just the number of negative eigenvalues. Now, I should mention that the case where d is equal to 1 and gamma is equal to half is settled by Timo Beidel, and the other cases were settled either by in the CLR inequality by those various authors, or in the original paper of Elliott, Lieb, and Walter-Thiering. And a surprising result, well, not so surprising here, but is that the CLR inequality implies the Sobolev inequality. So that is, if you have the case, the CLR inequality says that if this quantity here is less than 1, then our Schrödinger operator has no negative eigenvalues. And in particular, that says by the variational principle that the associated quadratic form is always positive, and therefore we have this kind of bound here. So if we now consider v in the following form in terms of some potential w, where w, the LD/2 norm of w is equal to 1, and you take any c greater than the constant in the CLR inequality, then of course this thing just implies this. And therefore it follows, by the boundedness of this, and for this u, that u, absolute value u squared, is in the dual space of LD/2, and that is dual in the Holder sense. Well, yes, and the p here is the dual Holder constant. And then you can find the bound, exactly that bound, on the from the Gagliard and Nuremberg Sobolev inequality. And of course, you can take c very close to LD, and then of course this is exactly the same thing. Of course.
So if you choose v as Hardy weight, it will be Hardy inequality too, right?
Yeah.
Can you say?
Yes, exactly.
But it's possible to choose such weight for Hardy inequality v, right? By condition or not?
Yes, yes, I think you're right. Yes, you could choose. Yes, it would, as long as this is. But no, this is not. As long as this is integrable in the case of the weights, then yes.
Okay.
Then this would, you would get a Hardy inequality here, given this, and in dimension greater than or equal to 3.
Okay, thank you.
You're welcome. Yeah, so basically, yes, CLR inequality implies Sobolev inequalities. And in fact, there are some more interesting kind of Sobolev type inequalities that one can deduce from the Liebscher inequalities in general. More surprising is this implication here. That is the result of Rupert Frank, Elliot Lieb, and Robert Siringer, that says that the Gagliardo-Nuremberg inequality actually implies the CLR inequality. Don't know where I got that L from. Yeah, so the opposite way around, it is also true, but of course this is in some weak sense where the constant isn't actually the same. Yeah? Otherwise we would know the constant from the CLR inequality was equal to the Sobolev inequality. Yeah, and the way that he did this was using kind of heat kernel methods that Yao discussed yesterday. So in terms of results in dimensions 1 and 2, but there are actually some kind of alternatives in the same sense that I discussed, kind of some alternatives in for Sobolev and Hardy inequalities. So in particular, this result by Calogero in 1965 says that now if you consider V to be some non-increasing potential on the half-line, and you consider the Schrödinger operator with potential V on a half-line with Dirichlet boundary conditions at 0, then the number of negative eigenvalues is actually bounded from above by this integral here, which has this exact right exponent for V. And the main idea of the proof actually in this case is kind of using the Sturm oscillation theorem, that is on the kind of half, if you consider the kind of eigenvalues associated to this Schrödinger operator, then the number of oscillations of bound states corresponds to the number of kind of negative eigenvalues. So your ground state, for example, is generally positive, has no kind of negative part, no oscillations. Your second eigenvalue would have second eigenfunction would have to be orthogonal and therefore kind of has some kind of one oscillation. Your third eigenfunction again has 2 oscillations, and so forth. And therefore, by looking at the kind of maximal, the last bound state on here, you can kind of estimate the number of eigenvalues. You can quantify the number of eigenvalues by the number of oscillations of your bound states. But it's kind of more complicated than that. There are some kind of scattering theory ideas in the proof, and yeah, yes, but that's kind of the general idea of why it works. So what I'm going to be talking about today, I'm going to be talking about work with Laptev and Schimmer that said in our work we have generalized this kind of Calogero type bound to operator value potentials. So that's a Schrödinger operator with some potential V, where V is an operator H point on the half line. And in this case, we're actually able to use it along with some some of the alternative Hardy inequalities to provide some CLR type inequalities in 2 dimensions. And I should say that some results in this were already in this kind of in the same sense already known, not for the operator value part, for the in 2-dimensional CLR type bounds, but none up until now were known with the kind of the L1 bound of the potential on the right hand side. That is V to the power of D over 2, where D is obviously equal to 2 in this case. And the importance of this is that we know the spectral asymptotics of the number of eigenvalues in this case. That is, if you consider some coupling constant on the potential, and you consider this coupling constant going to infinity, then we know that the order of the number of negative eigenvalues is of the order that coupling constant to the power of 1, or D over 2 in general, or in the case of trace bounds, that we also have sharp estimates for that too. So again, we're going to need one more idea that's very closely related to the variational principle, and that is if you consider some open set omega, and you consider 2 disjoint sets, omega 1 and omega 2, and such that the union of the complement of their union is of in omega is of measure 0, then the union, the LP space on the 2 space on the union is naturally isomorphic to the L2 space on all of omega. But we have the following inequalities, operator inequalities, in the sense of quadratic forms that I said earlier. That is that if the Neumann Laplacian and the Dirichlet Laplacian, that's the notation we're using here. The Neumann Laplacian is decreased when we consider this kind of splitting, and the Dirichlet Laplacian is increased, and that's owing to the kind of what happens to the domains. So if you consider the splitting here, then actually the Sobolev space H1 gets larger, because I mean, you can consider functions that are discontinuous on the boundary on the set of 0 measure, and it's easier to see that in the opposite case, where you kind of let your function go to 0 on the boundaries of each of these of omega 1 and omega 2, go to 0 is less than the H1 naught Sobolev space. Yes, and of course we can do this for kind of a general kind of sequence of open sets satisfying the same property, and obtain the following. So that is, if we split our domain up into k any kind of parts here in terms of omega k, then we actually decrease the size of our Laplacian here, our Neumann Laplacian, and therefore we increase the number of negative eigenvalues, for example, or the number of eigenvalues will stop below any point. So the main idea of our work is, so now you consider V some operator valued potential that's non-increasing, that is in the sense of quadratic form, since it's operator valued, and we can assume that each of at every point it's in some suitable class of compact operators on some Hilbert space H. Then we consider some weighting kind of F, that is some non-decreasing function, and we consider the following quadratic form with some Hardy term B. So you can kind of convince yourself, in the case where H is just taken as R, then this is just the standard quadratic form of the Schrödinger operator with the Hardy term B over T squared, and some measure here, some density here, F. And we can consider it's well defined on the space of compactly supported smooth functions, and we can consider its closure as the corresponding self-adjoint operator that it defines, and that is a Schrödinger operator with some Hardy term and Dirichlet boundary conditions on the half line with kind of values in this Hilbert space H. That is the following operator here. Now, if you consider the quadratic form, the associated quadratic form we just looked at above, you can split it into segments here. So you can split it into segments 2k plus 1 over all where k ranges over all integers. And of course, what one can now do using that V is increasing, V is non-increasing and F is non-decreasing, is that you can make it each quadratic form smaller by fixing V at 2k and changing F and dividing through by F in this way and making F 2k on the right hand side. Now, if you denote these intervals by ik, then each of the quadratic forms above, that is this part here, is a closed operator on H1 ik going into our Hilbert space H. That is, we can consider the corresponding self-adjoint operator hk that is now corresponding to Neumann conditions. So basically what we're doing now is doing that bracketing argument. So now we have a Hardy, some Schrödinger operator with Hardy term and some now some constant kind of potential on each interval ik, And now we're looking at it with Neumann conditions. We've already increased the number of negative eigenvalues by making it smaller. And now we're doing that again with this bracketing argument from before. So now we have a sequence of operators HK, and we're going to estimate the number of negative eigenvalues for each of these operators. So again, just using our variational formula here, we have the following. Then what we do is we just make a change of variables here. And what we pick up is an extra factor of 2 to the 2k here. And of course, our space just changes for each case, the Sobolev space on I0, that is the interval 1, 2. And again, what we do is now we make this this positive part with smaller. So we make the operator smaller again by picking s squared here to be equal to 2. And again, and now we have another upper bound on each of these, the number of eigenvalues of these operators HK. Pardon me. So now we have these operators, constant coefficients with Neumann boundary conditions, and of course now we can just we can consider the eigenvalues of this operator V at 2k, which is constant on this interval, obviously by our assumption, by what we've imposed here. And if we denote by its eigenvalues mu n, we know they're positive because it's a positive operator. Then we can, using kind of standard results, and again, you can kind of convince yourself in the case where H is equal to just real space is just scalar case instead of operator valued, then the number of negative eigenvalues is estimated with the following formula. And this is, if you're just looking at the real valued case, then you look on the Fourier series associated to the Neumann Laplacian. And so the problem here now is that normally we wouldn't be able to estimate the number of eigenvalues of Neumann Laplacian from above, but the key bit, the thing that comes in hand here now is this Hardy term. So what we're able to do now is, by using the Hardy term, we have that this expression here, where you divide through by m plus 1 squared, this should be, is bounded below by some constant. Now, then you can estimate this above by this, even further by this expression here. And now where you have m plus, we're just dividing through by m plus 1 squared and times equal by m plus 1 squared. And now again, you can consider, you can just consider on the space of natural numbers without 0, which is easily kind of estimated from above, just square root through there and so forth. And then of course, what we end up with is some constant times the sum of the square root, the eigenvalues for V. And of course, that's just the trace of the kind of squared square root, the notation we use for the moments of the eigenvalues. So now again, we use the V as non-increasing and that F is non-decreasing, and we assume again that the supremum is bounded from above, and we'll only kind of use 2 examples of that. And we can bound this above by the sum of the negative eigenvalues of each of these operators, and what we get is exactly this bound here. So that is what we have shown is that the number of eigenvalues corresponding to our operator valued Schrodinger operator with our Schrodinger operator with operator valued potential V, which is non-increasing, and with extra Hardy term with constant B, that we have trace a bound on the number of negative eigenvalues by the trace of B, square root of the trace. And of course, we can explicitly calculate this RB and the constant there if you want to. So how do we apply this? So this is the operator valued version of CLR inequality. And now how do we use an application? Well, what we do is, just in the simple case, we consider theta between 0 and 1, and then we split our Laplacian into 2 parts just by theta, and then we use Hardy's inequality on this part here, And then in terms of operator kind of these inequalities in the quadratic form sense, what we get exactly is, this shouldn't be a d squared dt, this should just be this should be 1 over t squared here. So what we get is some Schrodinger operator here with some Hardy term here. And so exactly what we will, so basically from any Schrodinger operator, from our Schrodinger operator here, sorry, from our Laplacian here, we can get a Schrodinger operator with a Hardy term, basically. And of course, when we divide through by 1 minus theta, then it doesn't change anything in terms of the negative eigenvalues because of the variational principle, apart from adding this extra term here on the potential, which doesn't matter because our bound is homogeneous with respect to the potential. So basically, now we know we can get an extra Hardy term through Hardy inequalities, and what we do is we apply this to the two-dimensional case. So now, if you consider this Schrodinger operator, operator value Schrodinger, so if you consider a Schrodinger potential operator on L2 on the half space with Dirichlet boundary conditions along x equals 0, then where v is a non-increasing function of x1, then you look on the operator value potential in this space here, this Hilbert space valued LP space, L2 space with you, and you take your operator, your potential equal to the Schrodinger operator on the x2 coordinate. Now you use the half-line Hardy inequality, which extends to functions like I mentioned with on H1 naught R2 plus, then on the half space, positive half space, and you apply the splitting scheme, and using our proposition, you find the following. Again, you have this extra kind of power here, but we don't really care about that. And you find the following. And now what you do is you just have the trace of the positive eigenvalues of this operator here. Well, that's just the same as the trace of the negative eigenvalues of the negative version of that, which is just the standard Lieb-Thirring inequality. And in this case, actually, we have an explicit Lieb-Thirring inequality constant for our Lieb-Thirring inequality, and this should be C here, okay, obviously. And what we get here then is the first result. And again, we did find a good value. Well, no, we didn't find a good value. We found a value for our constant here, but clearly it's far from the sharp constant that we kind of want in this case. So we can do this with half plane. The context of the next thing is that we can do it now for the Arohonov-Bohm magnetic potential. So if you assume A is such, then you look on the operator, the Schrodinger operator with the magnetic Schrodinger operator with potential V, where V is now radially non-increasing, and you look on the operator valued potential here with F now equal to R, then if you consider the operator value potential here to be equal to this this operator here, what you find is exactly the equivalent to this in polar coordinates, and here psi is just the flux of the AB field. So that is, you can, when you have the Arohonov-Bohm magnetic field, you can split it into some radial part plus some magnetic Schrodinger operator with constant magnetic field here. Don't know why my thing's going with. So that's exactly the splitting we use in this case. And here, of course, the Hilbert space is just the L2 space on the circle for the periodic interval. And again, we use the Hardy splitting. So we split the Laplacian here exactly using the Laptev-Weidel-Hardy inequality for Arohonov-Bohm potential. Yes, Dirichlet form. And so the proposition, yes, with F equal to R gives the following. So we have now that and I've used this terminology here for the Schrödinger operator. Here, we have the negative eigenvalues here of the Schrödinger operator with Aharonov-Bohm magnetic potential on the whole of the two-dimensional space is bounded by the trace of this magnetic operator with constant magnetic field. So then the question boils down to finding a Lie-Turing inequality for that operator, some trace bound. And of course, we didn't. It turns out that this didn't actually exist. So what we did was we managed to prove this bound here for a Schrödinger operator with periodic boundary conditions on some interval and with some constant magnetic potential. And actually, it turned out here that the magnetic potential was exactly what you needed to be able to bound this above by the L1 norm with D. In fact, if you had some integer potential here, or which corresponds to the flux of the Aharonov-Bohm magnetic field, then this constant here actually blew up. So this is exactly what we needed, and of course we were then able to apply this to get this CLR inequality with magnetic field in 2 dimensions. And again, here we could compute for any particular flux. Here we can compute the value of this constant here. And then finally, we were able to do this for the antisymmetric case. It was quite, in this case, the antisymmetric Lie-Turing inequality followed just quite nicely from the just the standard Lie-Turing inequality and some variational argument. And again, yeah, we were able to show CLR inequality in 2 dimensions for the antisymmetric Schrödinger operator with non-increasing potential. And yes, here are some references, and that is the end of my talk. Thank you.
Okay, thank you very much, Larry, for your talk. So if anybody has questions, please mute yourself and ask.
Larry, thank you for your interesting talk. I just have a curious question about, is it possible to apply or to have these methods to Hardy-Leray inequalities?
Sorry?
Hardy-Leray.
I'm not sure I know those inequalities, but
it's a kind of, instead of function, you have the kind of vector field.
Yes,
because they have uses divergent free, is antisymmetric.
Yeah, I think so. The key thing in this, the key thing with the Hardy weight here was that where am I? Was that it's exactly when you make this change of variables here, you get exactly the same 2 to the minus 2k from the Hardy term as you do from the change of variables in the kind of the gradient term. So I mean, I had a look at different Hardy weights. So I'm not exactly familiar with the Hardy inequality you're mentioning, but maybe you could send it to me, or I'll take a note of it and look at it. But maybe, I mean, we've also looked at whether you could do this for fractional kind of in the critical case for fractional Schrödinger operators. But in there, I think the Hardy inequalities are a bit more difficult and not exactly suited.
Also, I have a question about this. When you choose a 2k, it's why you choose is because of dyadic. So you choose.
Why you choose 2? No, you don't have to choose 2. So you can choose any. We choose a. When we compute the optimal constant, we compute it with a just any a greater than 1 to the power of k. But constant, the optimal constant for the in the bound here, where we used where we used A instead of 2, was actually the value of A, the optimal constant for A was the value of A was actually very close to 2. So and we're pretty sure that the constant here is not, well, it's not optimal. It's not sharp constant for sure, but whether this A sharp constant could come from this method, we think probably not. But yeah, so we did change it to consider different A and slightly different splittings.
Okay, thank you.
Thank you.
Okay, is there any other question? Well, I have a question. I actually got lost when you passed from the result in the half line, yes, to the half plane. I didn't understand how you transferred the result.
The half line to the half plane in the in this case.
Yes.
So, I mean, we consider here if you consider the potential here with the which is, so you have your gradient, your Laplacian term for the x1 coordinate. Basically, this should be x1, really, not t. And then you consider your potential v just as the other part of your standard Laplacian on L2. Now, I don't know, and then if you consider the splitting with the Hardy inequality, so Hardy inequality here with on the domain where the functions that vanish at 0 or along the whole line x1 equals 0, then exactly what you can get from this operator here is an operator with a Hardy term according to this scheme here. Because what you do here is you take the Laplacian here, you can just consider it directly from this, and then and you split it according to any theta, so 0 and 1, and again we optimize the constant over theta, and you get some extra term with Hardy. This obviously, again, as I mentioned, was false. It should be this term here. You get a Schrodinger operator with Hardy potential. So we're able to do that using the Hardy inequality on half plane, and then in that case we get exactly what we had before, where we just did the general result. But our operator now is the kind of just a Schrodinger operator on the x2 coordinate with potential here that is obviously dependent on x1, but we can consider it, constant in x1, and when we do that, the trace obviously is exactly the bounds, is exactly what is bounded in Lieb-Turing inequalities.
Okay, thank you. But
I don't know if that answers your question.
Yes, thank you. Then you could do the same for R3, like use the R2 plane to get the result in R3 like half, and then R4 and for any dimension.
Exactly. The problem is that there are already better results in that case. You have the standard CLR inequality, which.
But you recover those results by this procedure.
Exactly. But then we also have the restriction on the potential. So our potential would then have to be radially non-increasing, whereas the CLR inequality holds for any LD over 2 potential. So positive, yeah. So I mean, you could obtain explicit constants, but again, we get the. I haven't done it, but I get the feeling from this case that they're far from the optimal constants, and therefore there wouldn't be any use for the constants either.
Okay. Well, thank you, Larry.
Thank you.
There is more questions. If not, well, thank you again, Larry, for your nice talk. And then we'll have a 15 minutes break, and then we'll have the last talk of the workshop. So see you, all of you, in 15 minutes. Thank you.